start at it. I know we did this slide, but we're going to take a running start at it. We talked about 3 definitions of acids and bases, and they don't fight each other, which is kind of nice. But we're going to focus on this definition of an acid and a base. So this definition being the Bronsted definition, an acid is one that donates a proton, or protons, and a base is one that accepts a proton. Okay? And I'm kind of scooting forward a little bit. We talked about strong acids. Strong acids are ones that ionize completely. Okay? A one-way arrow, strong acid. And remember, we talked about this idea of, you're like, what in the heck is H3O+? And we talked about that's the hydronium ion, H3O+. And think of, like this slide kind of, these are all just review slides. Think of the hydronium ion as basically the same thing as an H+, same thing. And then we talked about weak acids. So actually, the fun chemistry is in weak acids. So weak acids only ionize to a certain extent. They go back and forth. It's in dynamic equilibrium, so we need a two-way arrow. So we show it ionizing, and then we show it kind of coming back. Okay, and we said anything in equilibrium, you can write an equilibrium constant expression, and that's exactly what we did here. And I didn't emphasize it on Wednesday, but I'm going to emphasize it now. So instead of just a normal Kc, we call them Kas. I guess I did because we said it's a lowercase a. It's a Ka, and sometimes I call it a Ka expression. And then here is kind of the counterpart here where you don't have, you're not showing that kind of carrier water molecule basically, which is kind of is happening behind the scenes. Now, weak acid. Okay, no, so now finally this is something a little bit different. So the Bronsted definition of a base is one that will accept a proton. Strong bases, I know you're like, what's that have to do with a proton? Well, I'll show you, but you probably already know. A strong base is one that can donate a hydroxide. That's one version of a strong base. Or provides, generates, is the word here, generates at least 1 mole of hydroxide ion for every 1 mole of that strong base. Okay, so an example of a strong base would be a salt that just dissolves in water. So for every 1 mole of sodium hydroxide salt you dissolve, you get 1 mole of hydroxide ion. Calcium hydroxide is also soluble. You get $2 for your bang. So for every 1 mole of calcium hydroxide you dissolve, you get what? 2 moles of hydroxide ion. Both strong, one-way arrows. So there are other bases, and I'm going to show you just one right now. But actually for every 1 mole that's in water, they provide 1 mole of hydroxide ion, but in a different way. What they do is react with water. Okay, so here we go. This is actually F oxide. It is a strong base, the one-way arrow, not an equilibrium. Basically what it's doing, if you compare this species on either side, basically it absconds onto one of the hydrogens and it forms ethanol. Is that not crazy or what? It forms ethanol, and from what's left over the water is a hydroxide ion. So again, we get 1 mole of hydroxide for every 1 mole of F oxide, which is awesome. Strong base. Well, a weak base then is going to be one that does not produce 1 mole of hydroxide ion for every 1 mole that's there. A weak base, we're going to see equilibrium arrows. So actually, we're going to show how this weak base interacting with water, okay, gives the hydroxide ion, but it's in equilibrium. So it looks like this. So the weak base, which is, it's not boron. Remember, the B is not boron. It's just some species. The weak base is actually going to be the proton acceptor here. It's going to accept a proton from that water molecule and form HB on the other side. And actually the water molecule in this case is serving as an acid, a proton donor. Right. This is called the deprotonation of water. Makes sense? You're taking a proton away from a water molecule. So, yeah, so we go ahead and show that in equilibrium. Again, you don't get 1 mole of hydroxide for every 1 mole of weak base because it goes back and forth. You can form that, but that is actually going to go back and form your weak base. So, again, we have a chemical equilibrium. We're going to write an equilibrium constant expression. It's going to be the molar concentration of the products raised to stoichiometric coefficients divided by the molar concentration of the reactants raised to stoichiometric coefficients. Liquids and solids do not appear in our Kc expressions, so they don't appear here. And notice we have a little subscript b there. Okay, so this would be the equilibrium constant expression for the hydrolysis of water with a weak base. So I think this is the same table that we looked at before. Those are, there are Ka's given, and remember we said on Wednesday that the higher the Ka, the more it favors the product side, and what's on the product side is what we call the ionized version. What's on the product side is the H plus that we're going to talk about on Monday. That makes it acidic. More H plus makes it acidic. So actually the higher the Ka value, the more acidic it is. And here are some bases, some weak bases. I think they're not all weak. No, they are. Let's see, what was I going to emphasize? When I was looking at this in my office, for instance, you can kind of quiz yourself. If you find, let's pick on diethylamine. If you find diethylamine over here, I'll put WB for weak base. Can we find it on the product side? And I say you can. Okay. If you find it on the product side, it's going to accept a proton. Can you see where, if you compare the formula of this guy, C2H5 quantity 2 NH, C2H5 quantity 2 NH2 plus. So do you see where that has picked up a proton? I mean, that's how I think of it. Okay, it's got a proton over there. So you have your weak base, and actually on Monday or Wednesday next week, we'll talk about those purple things. Those are actually a pair conjugate base conjugate acid pair. So we could do that for any of them. We could do this all day. Pick this guy, he's pretty easy. Compare him on the product side. And by the way, when we get rolling, do you guys buy this? For instance, if we pick on that last one, Kb is equal to the molar concentration of C2H5NH plus times the molar concentration of, I'm running out of room, the hydroxide ion, should be on one line, divided by the molar concentration of C2H5N. Does that make sense? Like there's a Kb expression for everything like that. Cool. So relative strengths of go like this. The lower the Kb, the weaker the base. So it increases strength here, and we're increasing strength of acid going up. So the title of this is some more Kb constants. Kb constants are ionization constants of weak bases. So these are proton acceptors. Okay. So, this kind of goes back to, I'm going to do a couple slides. This one's for Ka, the next one's for Kb. If you have, like the slide says, a substance that is, well, if we just go down here. If for a particular substance, Hb, if your Ka is larger than the Ka for just plain old water, okay, then it is going to behave as an acid. It will behave as the acid. I'll go ahead and put acid here, I guess. And in this case, your water molecule will behave as the proton acceptor, your base. How do I know it's a proton acceptor? Well, compare it on either side. How do I know this is a proton donor? Well, compare it on other side. Okay, and we'll talk more about the Ka for water. I think we'll talk more about the Ka for water next week. So if you have a substance, in this case not Hb, but a substance now is B minus, represented by B minus. And if the Kb for your substance, B minus, if it's larger than the Kb for water, then it's going to act as the base. So here we have it acting as the base, a proton acceptor. And here we have the water molecule then will act as the proton donor. All right, a few more terms to throw out there. If you have an acid that's going to be a proton donor and it will only kick off one proton, there's a lot of them out there. Like HCl is a monoprotic acid. Why? Because it's only got one proton it can kick off. H2SO4, I told you it's got two protons it can potentially kick off. So actually, in that case, it's polyprotic. So you can put HCl for the first one, H2SO4 for the second one. I don't know if these are very good examples. Polyprotic. Now HCl, you guys remember, is a strong acid. We'll put SA for HCl. H2SO4 is also a strong acid, but only the first proton kicks off 100%. And we'll talk more about this, but if you strip off one proton from H2SO4, you get HSO4 minus. And that one, you can kick off another proton, but the second one you kick off actually is weak. So you strong acided first, and then the second ionization is a weak acid for the second. That should do it. That's polyprotic. The other term to kind of wrap your mind around is amphiprotic. I love amphiprotic. So like if you can write with your left hand and your right hand, you're ambidextrous. Okay, good. Amphiprotic's kind of like ambidextrous. Amphiprotic is a substance that can be either a proton donor or a proton acceptor. And they're definitely players in acid-base chemistry. Amphiprotic, a proton donor, proton acceptor. It can go either way. And the way it's going to go depends on what other species there are in the mixture. The most common amphiprotic substance we've already kind of talked about a little bit. Actually, it's water. Water can be a proton donor and if it's a proton donor, it creates hydroxide. If it's a proton acceptor, it creates the hydronium cation. Okay, so it can go either way. In this case, water is being shown being a proton acceptor, a base. In this case, it's being shown being a donor, so an acid. I love it. And then the last one, this one, I have to think about this one. So the leveling effect, okay? If your medium is water, medium as in that's kind of the juice that your stuff is floating around in, because it doesn't have, not all solutions have to have a medium as water. Then the strongest acid you can possibly have actually is the hydronium cation, or the hydrogen ion, same thing. The strongest base is the hydroxide ion. So let's take a look at the homework that's due for Monday. I think I changed the name of it, so it's like cryptic. There, nope, that's not it. That's not it. That's it. So again, I don't know. I hope these hints are okay. So we have several substances, and you're supposed to say, will they behave as an acid or a base according to the Bronsted-Lowry definition of an acid base. So remember, for if something's an acid, look for it to be a proton or an H+ donor. If something's a base, look for it to be a proton or H+ acceptor. So my hints a year ago anyway was I said, so for instance, take the first one, HNO2. Does it seem reasonable that it's going to either, in the first case, kick off the proton, being acid, from H+ and NO2-, or is it going to accept a proton and form H2NO2+? How many people think it's more likely to be an acid? It just seems, it makes more sense, doesn't it? And you're right. You're right. But the other thing is actually, and this makes probably more sense, is, I think this is part of my hand. Oops, sorry, go back. Is if you look on the tables that I gave you in your notes, look on the table and find HNO2. I dare you. You have to get on your magnifying glasses. Look really closely. And I bet you can find a Ka value for it. Okay, good. If you can find a Ka value for it, it makes a pretty good weak acid. Okay. I thought I had another hint. Let's see, what if I do this? It just goes on to the next one. Okay. But like, for instance, D. Okay, look at D. NH4+. Do you think it's going to donate a proton? Yeah, it's probably going to kick one off. It's going to donate a proton. Yeah. It's going to act as an acid. If NH4+ donates a proton, what will it be like? What's on the product side? What goes here? Yeah, NH3, exactly. Some other teacher picked up a blue one. I don't know if it's legal. Exactly. So this is acting as a proton donor, so it's acting as an acid. So C looks like it's going to want to accept a proton, doesn't it? Mm-hmm. Yep. And then I have down here which is larger, Ka or Kb. So I must be able to find these in the table. Some, but you won't find NH4+ in the. You wouldn't find it in a Kb table. Anyway, let me see what the next problem is. There's only two problems. The other one is this one. Yeah, and these are both odd problems, so you should have the answers if you want to take a look. For each of these, identify the acids. You should find an acid and base over there and an acid and base over on the product side. Let's see if I had any hints. So, for example, I kind of did the red matching up and the blue matching up. That makes sense. But then you should look at it going back the other way too. Okay, so if you go back the other way, for instance, it looks like the H3O+, the hydronium, is actually donating a proton, so it's acting as the acid, and the the OBr minus the hypobromite is actually accepting a proton, so it's acting as the base. So they're all kind of fun. That's it. Wait, is there one more hint? Oh, you guys don't need that. Okay. Oh, anyway, it's the same one. Okay. There you go then.